All right, first of all, I would just like to say thank you to the Scientific Organizing Committee for putting so much effort into running this workshop, and to Jeff and Christoph for setting up the hands-on sessions, and of course for all the help from Ellen and Roberta, Dawn and Irene, and any other people I may have unintentionally left out. So as Roberta said, my name is Christian Clanton, and I'm a fifth-year graduate student at The Ohio State University. And in the next 10 to 15 minutes, I'll discuss the first study to combine the results from 5 different surveys using 3 different independent exoplanet detection techniques: microlensing, radial velocity, and direct imaging. So I'll just start off by showing a familiar diagram of planet mass versus separation. And on this diagram, I'm showing the roughly 150 confirmed planetary companions to M dwarfs from the NASA Exoplanet Archive. And also included on this plot are rough schematic representations of where each of these different detection methods that I've included where they're sensitive to planet detections. And in this work, I choose to focus on M dwarfs for a few reasons. The first of which is that they're simply the most common stars in our galaxy. And also, the constraints that we have on exoplanet demographics from microlensing exist primarily for M dwarfs. And as Matthew mentioned yesterday in his talk, this is due to the fact that the rate of microlensing events explicitly depends on the lens mass function, which is weighted towards lower mass objects. And finally, there are several existing demographic constraints from other techniques with which we can compare. So now I'll just briefly summarize some of these results. So here I'm plotting planet frequency as a function of planet mass and semi-major axis. And this is a plot that Scott gave a preview of on Monday, but I'd just quickly like to sort of go through this again as it's relevant to the study at hand. So radial velocity surveys have found a frequency of giant planets that is quite low. And this has been heralded as somewhat of a victory for core accretion theory, as this rate is significantly lower than that inferred for higher mass stars. And I'll just quickly note here that the vertical error bars on these points are the uncertainties in the measurement of the planet frequency, while the horizontal bars represent the approximate ranges in planet mass or semi-major axis over which these measurements are made. Now, on the other hand, microlensing finds a frequency of giant planets that is more than an order of magnitude larger than that inferred by radial velocities. And also included on this plot are upper limits on planet frequency from the Planets Around Low Mass Stars, or PALMS, direct imaging survey. Now, just looking at this figure, it's not exactly clear how you compare each of these results, because as we've learned throughout the week, each technique introduces its own unique and intrinsic observational biases and selection effects that you must take into account. And that's precisely the point of my work, is to develop a comprehensive picture of exoplanet demographics by combining or synthesizing the results from the various detection techniques. And so on Monday, Scott talked about our comparison and combination of microlensing and radial velocity results. But today I'll tell you about another project that we're working on to also include the results of direct imaging. And specifically in this project, we're looking to place constraints on the long-period planetary companions to M dwarfs. So these are planets beyond just a couple AU. And as I mentioned, we compare with the results of 5 different surveys. So on the side of microlensing, we include the results of the Gould et al. 2010 survey, who measured an integrated planet frequency over a range in mass ratios and projected separations. And we also include the results of the Sumi 2010 study, to provide a measurement of the slope of the mass ratio distribution function. For radial velocities, and in particular since we're interested in constraining long-period companions, we include the results of the CPS trend survey reported by Ben Monte just last year, who find the detection of 4 significant long-term radial velocity drifts that they then followed up with AO imaging and found no companions down to covering most brown dwarf masses, strongly suggesting that these trends are the results of giant planets. And finally, on the direct imaging side, we include the results of the PALM survey, which I mentioned earlier, but we also include results from the 16 M stars imaged as part of the Gemini Deep Planet survey and reported by Lafreniere in 2007. Now, neither of these surveys actually found any planetary companions, but as Beth mentioned yesterday, there's information in these non-detections, and we include these as well. So the primary objective of this study is to ask and to answer the question, is there a single planet population that is consistent with the results of each of these surveys? And so to tackle this problem, we start out by assuming a distribution function here that is described implicitly by 4 free parameters. So So we have the slope of the mass distribution function alpha, the slope of the semi-major axis distribution function beta, the normalization of the function, and finally an outer cutoff radius for the semi-major axis distribution. And so we start out by generating random values of these parameters and generating a population of planets from this distribution function, which gives us a set of planets that are now described by masses and semi-major axes. The next step is to map these properties into the observables relevant to each of the techniques to which we compare. And so for microlensing, this means we need to get a planet-to-star mass ratio, Q, a projected separation in units of the Einstein radius, S. And in order to do this, we must adopt a galactic model and a lens mass function in order to get the relevant parameters such as the lens distance and the lens mass, as well as kinematics for the lenses. And we must also generate orbital parameters for each of the planets in order to project the orbit and obtain our observables. On radial velocities, and again, since we're interested in the trends, we must determine the orbital period of each of the planets. We must also determine the acceleration that each of the planets would induce on their host star. And so to do this, that requires knowledge of the host masses, and again, we must generate orbital parameters. For direct imaging, we need a difference in magnitude between the planet and the star, which means we must adopt planet evolutionary models and have knowledge of the ages, or at least some knowledge of the ages, and distances to the host stars. And again, since we're trying to project the orbit, we must generate orbital parameters. There's a lot of work that goes into this, but I've only got a short amount of time, and if you have questions, please feel free to ask me later. So once we have all of these observables, we compare them with the actual detection limits and sensitivity limits of each of these surveys in order to determine the number of expected detections for each of these surveys, which we would then compare with the actual reported results and generate a likelihood for this particular planet population based on the actual survey results. And here I'm just showing examples of the various types of detection limits which we've seen somewhat throughout this week in other talks. So once we do this, we then repeat this analysis many, many times in order to build up constraints on these 4 parameters that describe our planet distribution function. And these are weighted according to their likelihoods given the results of each of these surveys. So when you put everything together, these are the results that you get. And so just quickly, the solid lines represent what we get when we assume hot start planet evolutionary models, while the dotted lines show what we get when we include cold start models. And the darker of the 2 lines is the 68% likelihood contour, while the lighter of the 2 is the 95% contour. And so it actually turns out that the microlensing results alone are able to pretty well constrain alpha, the slope of the mass distribution function, and the normalization of the distribution function quite well, to the point, in fact, where these values are more or less fixed. The addition of the radial velocity constraints places a lower limit on beta, the slope of the semi-major axis distribution function, such that you actually distribute enough planets at long enough periods that they would show up as trends in the radial velocity surveys. Now, unfortunately, radial velocity surveys can't actually place an upper limit on the slope of the semi-major axis distribution function beta, because there's a degeneracy between this parameter and A out, the outer cutoff of the semi-major axis distribution function, such that you can change beta and A out in ways that you always preserve the number of observed trends. And it turns out that direct imaging surveys suffer from the same degeneracy, and so you're left with relatively less constrained values on beta and A out. And so now I'm showing the one-dimensional likelihood functions on each of these parameters. And again, you see that alpha, the slope of the mass function, and A, the normalization of the distribution function, are relatively well constrained, while there are large allowed ranges for beta and A out. Now I want to draw some attention to this feature here in the likelihood function of A out. And so what this has to do with is direct imaging surveys are completely insensitive to planets that lie within their inner working angles. And so at the typical distances for stars in the GDPS and the PALM survey, this turns out to be some 10 to 15 AU. And so regardless of what your values of alpha, beta, or A are, as long as your outer cutoff radius is within this inner working angle, then since these surveys actually detect no planets, you're always consistent with their results. And so this is what gives rise to this feature out here, and you have large allowed values of beta, the slope of the semi-major axis distribution function. But you'll also notice that there's a tail out to larger outer cutoff radii, and for this to be allowed, you actually have to have smaller values of beta such that you don't distribute too many planets in the detectable regions of the direct imaging surveys. And so what this all means is that yes, indeed, the results of microlensing, radial velocity, and direct imaging surveys can be described by a single planet population that is described by a very simple joint power law function in planet mass and semi-major axis. And here I'm just showing the resultant median values and their 68% confidence intervals. So some ongoing research that I'm currently working on is to ask the question, is this population that we found that's consistent with everything else, can this also explain at least a fraction of the short timescale microlensing events that Sumi et al. Identify and argue are actually due to free-floating planets. So the question here is, are these things actually bound? And if so, are they explained by the same population that we find is consistent with all of these other surveys? And again, in the future, another thing we hope to do is include results from the Kepler mission and really complete sort of the synthesis of all of these different types of results, covering the big four, as Scott mentioned in his talk, of microlensing, radial velocities, transits, and direct imaging. And again, in the future, and this is related to what this entire conference is about, we'd like to compare our demographic constraints with the output of planet population synthesis models, such as those by Christoph Mortacini, Shigeru Ida, and Doug Lin. Now, before I conclude, I just want to take a moment to emphasize the importance of synthesizing results from multiple detection methods. Comparing the output of planet population synthesis models to the results of a single survey or mission or technique can provide clues to how planet formation works in these specific regions of parameter space that are covered by that survey or technique or mission. However, in order to get as we've seen throughout the week, changes in the input physics to these planet population synthesis models affect not only limited regions of the parameter space, but in fact, much or even all of this parameter space that is covered by all of these different surveys. And so the only way to develop truly comprehensive and observationally constrained planet population synthesis models is to combine their results and compare with those combinations. Thank you. So the question was, one of the difficulties in comparing results from different methods is that typically you tend to probe different samples of host stars, and so the question was, how do we handle the fact that these surveys might be probing different populations? And the answer is that we kind of don't. So the masses that we use when we derive the observables for radial velocities are the mass, since we're comparing to specific surveys, we take the masses and their uncertainties from those surveys and apply that to those stars. For microlensing, it's a little more complicated because we don't actually measure the masses of most of the lenses, and so we have to, as I mentioned, adopt a galactic model and a lens mass function in order to generate the distribution of lens masses there. And then for direct imaging, in most, if not all cases, we're not sure what the masses are, but in that case, it doesn't matter so much. But what I can say is that the typical host star mass for microlensing is something between 0.3 and 0.5 solar masses, while the median mass for the CPS trend survey that we compare to is about 0.41 solar masses, and the median mass for the HARPS South survey to which we compare is something like 0.3. So while their distributions might differ, their median values are roughly similar, and so we just kind of go with that. Yes. So the question was, it's not always, it's very hard to get ages for M stars, and so Beth was asking if we take the uncertainties on those age estimates into account, and the answer is yes. When we generate our planet population, we do this many times, and so for each planet of a given mass, you marginalize over the uncertainties in the ages, and so the age estimates that we have come directly from the surveys themselves, and so some of them are more well constrained as they're in moving groups or something like that, but some of them just have a pretty wide range of ages, and so in that case we just assume a uniform distribution across that age and then draw from that as our prior on age. So the question was, have people compared the planet distribution functions, I guess, that have been inferred from the Kepler data with those inferred from radial velocities and other techniques? And one answer that I can give you is that in Scott and I's work, when we combine microlensing and radial velocities, we don't compare with we don't actually derive in that paper a distribution function for the parameters of the planets, but we do get frequencies in various binned regions of planet mass and period, which we compared with the results from Kepler. And we actually found that in the regions where they overlap, there seems to be consistency between the two inferred frequencies.
So we're looking at a subset of, because the lensing surveys probe mostly M stars, you're looking at the Kepler data that's just for the M stars.
Correct. Yes. So Joe was saying that since microlensing exists, the constraints for microlensing are primarily for M dwarfs. He was asking if we're just looking at the Kepler M dwarf sample, and the answer to that is yes. And also for the radial velocity surveys we include, those are also M dwarfs only.